Hello, everyone. This is probably one of the few sessions of GTC that is focused primarily on hardware, but we want to kind of skirt right at that exciting software-hardware interface where if you don't look carefully, one leaves a lot of performance on the table. My name is Anand Iyer, Product Planning Director at Samsung Semiconductor. I'm focused primarily on various compute workloads, processors, and accelerators, mainly for their impact on memory and storage, both future product evolution and market demand. And I'm here to welcome Dr. Dan Ernst, a distinguished technologist in Hewlett-Packard Enterprise's HPC and Mission Critical Systems Advanced Technology team, where he leads the investigations into future high-performance computer architectures. Dan, hello, and thank you.
Hello, Anand. Thanks for having me.
Absolutely. Okay, a quick intro. Dan was part of the recently acquired and the brilliant Cray team, which won all the 3 exascale big projects for DOE. Congratulations on that, Dan.
Thank you. We're super excited and very honored to be involved in those projects.
So he's been focused on application optimized compute and memory system architectures for future AI and HPC converged clusters. And that makes him a perfect man for this hour, where we plan to tease out where HPC and AI converge and diverge, both on application as well as hardware architecture. From there, we're going to dive into performance as well as challenges in compute and memory on these clusters, and then wrap up with some discussions about what the future holds for processors as well as memory in this exciting area of accelerated computing. First of all, Dan, thank you so much for making time for this session amidst the challenging time we're in. It's been a challenge, to say the least.
Yes, it's been a unique time and challenge for everybody in a lot of ways, but also a lot of exciting things going on.
Yeah. So along those lines, just recognizing where we're, the times we're in, I'd like to open up this discussion by requesting you to share one interesting activity that you may have seen among the many, COVID simulation and modeling areas.
Yeah, it has really been pretty exciting. There's a lot of people in the industry across, industry, academia, national laboratories, and government trying to have an all hands on deck moment here, where scientists realize, hey, we can have an impact on trying to address the sort of the crisis we're in, right? And so we've seen this in the HPC space and the AI space, really looking at pushing forward on ways we can treat or prevent, the spread of the coronavirus. So a couple of examples, right? Work at DOE labs has been focused very much on compound analysis, so very large-scale simulation of proteins and trying to understand how they would interact with the virus itself at really low and detailed levels. What's interesting about those simulations is that they're trying to be a precursor and a pre-screener in many cases for people who actually have to do experimental science. So, for example, some of the folks at Oak Ridge went and did a study of trying to find a large number of compounds. They went through a lot of different chemical compounds trying to look at interactions as a way of sort of pre-filtering and coming out with a small set that would then be sort of sent over as really interesting candidates for folks in wet labs, right, in the experimental world to try out and start to work towards. So, that's one example. There's others of using AI, for example, to do image analysis of X-rays and trying to do diagnosis. It's really been end to end, but the theme running across all of them is they need a lot of high performance and accelerated computing to accomplish them. And a lot of our our partners and our customers and even our competitors have gotten together and tried to make as many resources available as possible to those scientists so we can try and make these advancements as quickly as we can. Pretty exciting time.
It's amazing. So staying on that topic, Dan, on the application overlap between the simulation world and AI, can you go a little bit deeper into an area where bringing in like a ML or AI techniques has profoundly improved results or convergence time or whatever, right, in an important HPC area.
Yeah, I think this convergence is something that the industry's been talking about for several years now, right? Um, and what it comes down to is really, incorporating data into simulation and vice versa, right? The high performance computing world has been really focused for many, many years on trying to do the simulation portion of this because it was the area that the most effort had been expended and also the most benefit could be gained. And what was learned over time is that by taking advantage of data analysis at various stages, um, there are things that we could do both on the front end and the back end and within these simulations to try and either improve performance or to get more insight out of them, right? So as examples, right, we've seen workflows now in many of our customers, and we're seeing an increasing demand for these kinds of capabilities to, within a system, run AI workloads to do, for example, preconditioning on a simulation model, right? So that these simulations will have to do a whole lot of differential equations, right? And they're trying to find solutions, and those solutions take time to converge, right? And the amount of time it takes to converge is actually quite dependent on how good your initial guess is, your initial conditions. And so there are a number of places that have taken a look now at what we like to call cognitive simulation, where we're looking at finding ways to use AI to improve that initial condition so that the convergence time is a lot faster, right? So that's a performance improvement question. There's a project working in a partnership between Argonne and Cambridge University where they were looking at materials for interaction with solar power generation, and the materials they were looking at, the way they did a pre-filter was actually by generating a database of chemical properties out of academic articles, right?
Wow.
They use that. Yeah, it's sort of not the place you would think. It's a pretty noisy channel, right?
Wow.
But they were able to generate an interesting database and then do pre-filtering to filter down to a small number of candidate materials that they could then go and do simulation at scale. So those are all some areas where we've seen this interaction. That's a very tight interaction between simulation and AI. And
Yeah.
that's not even talking about the back end, right? Where simulations generate enormous amounts of data, right? They could generate image data or over time, there are efforts to look at that as well, coming out the back end and trying to get more insight out of that, find patterns in that data that perhaps give us new insights into the behaviors of materials or processes,
Right.
or even could be used then to turn around and make further simulations faster, right? By understanding what came out of the last one. So all of these are advancing very quickly. This is all stuff that's happened even just the last few years.
Yeah.
Um, so it's again, an exciting area and an exciting time, but it's putting a lot of pressure on what we do as a system company.
Right. And for us too, as commodity, memory and storage suppliers, right?
Yep.
So that's kind of interesting. I mean, you talked about imaging data, right, as a key, area, which is pushing data size. But if you remember, like 5-6 years ago, when this whole wave of AI 1.0, I'd like to call it, kind of took off, it was just, ResNet and all these vision-oriented models beating human-level accuracy. But if you look at what's happened recently with language modeling and language generation, the data set size from vision seems like nothing, right? I mean, these things are now climbing exponential, and most recently, Microsoft did this model with like, I think 14 billion parameters, and they had to use like 128 voltas, in parallel. These sorts of data sizes are, nothing for you guys, right, in the HPC world. But whether you're trying to model climate or nuclear weapons and whatnot. But what I wanted to kind of get into, once you kind of leave out the big, massive labs, which have obviously a lot of people and infrastructure dedicated to these problems, but you also sell to a lot of enterprises, right? So I want you to take a minute to kind of talk about this whole problem of, problem size, right, in their industries, whether it's, oil and natural gas, or, pharmaceutical, or even financial, services. How, talk about the process that your customers go through when they look at, one of their big data set size problems, and then the decision of going to a supercomputer style architecture, not the system itself, but the process, right? What goes through with enterprises when they kind of decide, okay, we've got to go to something different to go and solve this. If you can talk to that, Dan.
Yeah, I mean, there's both a sort of a technological and as well as a business argument, right, that has to get made for people to make investments in computing, right? On the technological side, what most of these people are looking at is capabilities, right? What is it that I can do now, that I can learn now, that I can understand now, that I couldn't without um, this high performance computing capability, right? And I'll point to oil and gas as an example. What was learned, a number of years ago, we partnered with a company by the name of PGS, which is a large oil and gas services company that helps with this issue in particular. And they found that going to a larger, more distributed, um, you know, arrangement with their problem size was a way for them to get a capability to locate things better than anybody else. Right? They increased their capability and accuracy by a large amount by going to this more parallel, more large scale model. Um, that has impacts on a couple of things, right? One of the things obviously is the size of memory, right? The size of your data set. Um, as you're thinking of capabilities, um, you could do one of two things, right? You could have a capability you have now and do it faster, right? And that's accelerating one direction. Or the other direction is you could have, in the same amount of time, you could solve a bigger problem, right? And solving a bigger problem usually means an increase in capacity of things, right? How you solve that is either adding capacity on every given node, but it could also be adding capacity across the system by just scaling it to a larger size, right? Um, and that's what a lot of our customers have done historically, right? Is they're trying to move to a new capability at a larger, solving bigger problems in a tractable amount of time, right? They increase the system size, they increase the memory footprint, they increase the amount of compute, and they try to do it in a balanced way, or the ratios you need for the next problem size up, right? And the machine learning world is kind of going through the beginnings of this now, right? They've started with things that were tractable, and really the explosion started because getting to reasonable, accuracy wasn't something that could be done until we got to a certain point in hardware compute, right? And once we got to that point, it became useful. It became, something that everybody wanted to do. Now, we've advanced, as you say, towards sort of AI 2.0, right? People are learning that, oh, there are hardware capabilities in a scaling sense that they haven't tapped into yet. And what could those be used? Language generation and other generative operations, I think, are a big area that we'll see, that pressure happen, as you pointed out.
Yeah, it's kind of fascinating, right? And that brings us to this next section, which is, the core of our topic, which is the compute hardware itself, right? We recognize this as a GPU conference, but we also need to acknowledge that graphics processors, to kind of as a main compute element for general purpose parallel computers, a relatively recent thing, right? And this is largely developed in the HPC ecosystem, by NVIDIA, as well as with help from, folks like you, right, at Cray. So, one thing that you mentioned, while the problems are intractable in this domain, and you kind of need this, hybrid approach, right, where you absolutely need that scale, to minimize, the communication overheads, you kind of go the scale up approach. But at the same time, one thing I wanted to touch on, Dan, this sort of parallel compute itself is a challenge, right? But then you, on top of that, you layer on, heterogeneous compute, right? So scaling with just CPUs and the flops that you get from CPU is one approach. But then you're talking about GPU, and now people are looking at, accelerators, right? Just focused on AI inference and what have you. So, how do you look at the balance between, programmability and development time, right? When you look at heterogeneous compute, and just vectorization is a problem in and of itself, right? Even though GPU compute has been around, the amount of workloads that have actually migrated in DOE labs is still under 50%. So talk about, the challenges of parallel programming and heterogeneous compute from the point of view of the developer, right? And then also, if you kind of know of anything, happening, right? Intel was talking about this, merging this development environment using, new tools, right? Is there a tip over point in your view that's coming where the developers can just focus on, the problems that they're solving and not worrying about memory management or, more efficient vectorization or what have you, right? But, between heterogeneous processing elements. If you could touch on that.
Yeah. Yeah, this is an interesting problem, and one that we've been wrestling with for a good, almost a decade now, right? We deployed with NVIDIA, we deployed the Titan supercomputer at Oak Ridge, and I think it was 2012. And that system was sort of the first real at scale HPC system based off of GPU, right? With our, at Oak Ridge National Labs, who put in an enormous amount of work in trying to understand, if and how they can get applications onto that heterogeneous architecture, right? And we learned a lot on that system. A huge amount of productive science got done. But as we took that sort of, partnership and over the years saw successes out of it, moving it into the broader market was a challenge, right? And part of the reason for that is, as you touched on, was it took time for people. If you think about it from an investment standpoint, right, as a business or a lab right, you have costs of hardware and costs of software, but then you have costs of developers, right, and how much time developers have to spend to get performance, right? And the DOE labs made a calculation that spending more developer time was worth it to get it to the capabilities that they could get at the high end, right? With using accelerated computing. What we've seen since then is that there are some places that have made that and decided to make that investment, right? Most of them have been capability computing centers. Huge advancements have been made in the last few years around making things more accessible. As you mentioned, trying to get to the point where users can just deploy and not worry about getting the last bits of performance out of their code. And there's two ways that that's been done. One is just time and a development of a code ecosystem, sets of libraries and other tools that allow people to just call a function to do something instead of having to write it from scratch. But the other thing that's happened is we've started to see successes with domain-specific languages, and this is a case where AI has done great things. If you look at infrastructures like TensorFlow, right, where you can express a neural network pretty clearly without a whole lot of thinking about the underlying architecture, and then that can get deployed, at a pretty solid amount of performance without too much work, because there's a layer in between where the mapping can be done pretty effectively by software. And that's something that AI has done really well. In the HPC science space, we've started to see some of our customers work on similar kinds of frameworks. It's a little harder because in a broader HPC sense, the diversity of problems is still pretty high, right? So having a domain-specific language is a little tricky when your domain is really big, right?
Right.
So that's something that they've been wrestling with. But there are definitely folks that are writing new code and are willing to take the leap and get the performance out. It is getting easier. But again, there are also places where they have made the other side of that decision, right? And I'll take as an interesting data point NERSC, right? NERSC has been a CPU shop for a long time. And if you look at their user base, they have thousands of users. They are really a central place in the US for open science. So they have a massive number of academic users running tons of different codes, right? If you're looking for a place where updating your codes and making performance improvements to your codes, an investment at NERSC is a huge statement because um, the total number of applications they have is so large, they just can't scale that optimization work, right?
Right.
Well, the fact that their next generation system is going to have NVIDIA GPUs in it should tell you that they think there's enough software that's already been ported, that's available, that's easy to use, that they think their users will use it, right? And they have data they've put out in their reports to back it up. So progress has been made, and we are seeing a lot more in the last couple years uptake and acceptance that there is accelerated computing is something that may be feasible to do, if as you generate an ecosystem.
Yeah, I mean, that makes sense. I think, bottom line is, right, whichever way you look at it, whether it's HPC or just your typical vanilla data center, problems. I think the one thing that people can kind of put their finger on is that the compute density is climbing, right? And with that, how do you move the heat from this density, and how do you power these massively powered, processes, right? It's a
Yep.
challenge for everybody. And there was a point in time where everybody said Moore's law is dead, but if you start listening to Jim Keller, right, of Intel, he's pounding the table and saying, look, EUV is solving a lot of the challenges from density scaling, at least, right? And he's projecting just vanilla density to keep climbing as far as the eye can see. So what I wanted to, you talked about the power density problem, right? If you can get a little bit deeper into, tease out a bit more on this topic, Moore's law is going to continue to give a lot more, cores per GPU and a lot more CPU cores per socket, right? So can we keep going, provided, the foundries can keep delivering area density? Can we keep going, or are we pushing against some fundamental limit on, and again, I mean, this comes down to like the cost versus, you can solve, given unlimited resources, you can solve anything, right? But is it practical for your enterprise customers, for example? And this argument holds good for the hyperscalers as well. So liquid cooling is one way to kind of, solve some of the thermal challenges and keep pushing, right? Are we at a point in time and maturity with liquid cooling where your mainstream enterprise customers and the cloud guys for general purpose compute, can they deploy it in their normal, high volume racks? What do you think about liquid cooling and its maturity?
It's made a lot of progress in the last few years, and I mean, jokingly, I'd tell you we've been doing liquid cooling for almost 50 years, so it should be mature by now. But more seriously, it, people everywhere are seeing this pressure, right? Um, and and it's brought about. Liquid cooling is one example. Higher efficiency power delivery is another example of technologies that have started to move, and industry, businesses that have started to move. Um, standard rack adding in, fairly low cost liquid cooling components is something that has been in a pretty good place for maybe 4 or 5 years now. We declared some of we deployed some of that in our cluster environments, a number of years ago, just as a commodity rack solution. But those only get you so far, and what we're seeing from a roadmap going forward is, to the process density question. It may be that we're getting more per piece of silicon, but the other advancement that's happening in the industry right now is the fact that more silicon is going into sockets. That packaging within a socket has increased, by a factor of multiples in the last year or two, and is going to continue that direction going forward. That's where a lot of the process technology innovation is happening right now, is packaging. And that's allowing a lot more silicon and a lot more compute and memory to go in a more tightly coupled manner, right, in the socket. Now, if you look at that from a, I guess the way to think about liquid cooling in the past was, why would you need liquid cooling? What benefit does it get you? Because liquid cooling does cost you something, right? But what we're seeing in architectures going forward is that the benefit of what you can run with and what you can put in a package, if you have liquid cooling, way outweighs that cost. It's a getting to be an order of magnitude kind of a performance density argument, and that makes it really, really interesting and really worthwhile. Then we need to be higher density, right? Really, the first order motivation for liquid cooling is not necessarily that density, but it's the ability to cool these increasingly hot CPUs and GPUs, right, going forward, and other accelerators. We've seen on forward-looking roadmaps sockets that are a kilowatt, right? People want to do that kind of thing. Right? So that's what really led us to design the Shasta infrastructure that we did, which is capable within a cabinet of somewhere in the order of 300 to 400 kilowatts, right? Both power delivery and cooling.
It's nasty. You compare that to a typical data center rack, you're talking 13, 14, 15 kilowatts, right? And even that's a bit of a challenge to move that heat.
Yeah, it's an order of magnitude, and it's a closed system, right? It really puts very little pressure on your data center in an airflow and HVAC perspective. There are requirements you have to have around power. Obviously, that's a lot of power, but for the most part, it is going to be sort of the price of entry in HPC going forward, right? You're going to need to have enough density and enough cooling capacity to get these these very hot parts and make them usable, right?
Makes sense. Let's go a little bit deeper from there, right? And you mentioned already kind of tightly coupled memory, and so let's touch on memory, and and some of the challenges that you articulate, right, with cooling and power. It also has a substantial impact on memory. One thing that a lot of people may not realize is memory is the second most expensive component in overall in data centers as well as HPC systems, right? I mean, in fact, I think I read somewhere Google actually mentioned that 50% of their hardware infrastructure spend is actually on memory. So HBM especially, right, high bandwidth memory, it's an expensive piece of memory silicon, and it's for you guys as well as for us, right? But it solves, like you mentioned, a very unique problem for parallel compute and HPC and AI in particular, right, where you need your bandwidth limited, and you need screaming bandwidth, but at a relatively low energy consumption, because cooling is a problem, power delivery is a problem. So wherever you can solve these challenges, you guys would happily take it. And Dan, you've published some interesting results on the right mix of the different memory types, right? Whether it's high bandwidth memory versus high capacity memory, going all the way to like persistent memory, right? These new emerging memory types. So can you touch on the learnings that you've had for the set of problems that you looked at, Dan, and how and then how this learnings has shaped your node architecture, right? For both for the recently announced exascale systems as well as the enterprise systems that you guys built.
Sure. The way to think about it is we took an application oriented approach, right? We went back 6 or 7 years ago, and we have performance engineers who are trying to understand the performance of different applications, right? And they were looking at sort of some speculative future architectures, and trends in how things were moving, right? And this is in the time frame of early Xeon, Sandy Bridge, Ivy Bridge, right? And as they looked forward through sort of an Intel roadmap, which was sort of the only game in town at the time, what they were finding was looking at a broad pool of HPC applications, 30 or 40 different applications, and then trying to project how they would perform. They saw the trend lines moving in a pretty worrying direction, right? One was, well, their application performance seemed to map pretty well to memory bandwidth. Right? That was the limiting factor in a majority of what they were seeing. What they were seeing in the architecture trend lines was that memory bandwidth was going up at a pretty small rate, right? You can think about, the typical CPU roadmaps where, every generation memory bandwidth goes up 15 or 20% over time, right? What we were also seeing is that those roadmaps were adding more cores. They were also adding improvements in more floating point, right? And this is even predating some of the AI work where this was pushed on even harder. But we saw flop rates going up very quickly. But what we saw for applications was that they were not really tracking that at all. Right? It was very rare for an application to be able to actually take advantage of flop rates in those kinds of situations. So that led us to look really hard at memory. And when we started working with DOE on exascale investigations about 7 years ago, one of the topics we looked at was memory architecture, right, of a future exascale system. And if you were look at workloads in the HPC space, we said, look, going forward, we would like to have a memory bandwidth to floating point, ratio that reflects some of the most productive architectures at the time, which was about 0.2, right? So that's 0.2 bytes per second per floating point operation per second, right? Not fantastic, but it was, at least as good as we had at the time, and people were having pretty good luck with that. Well, if you extrapolate that forward into an exaflop system, right, an exascale system, that means you need something like 200 petabytes per second of memory bandwidth. And so you can do a little experiment, and we did that, where we did the math on this and said, well, what does that memory system look like that delivers 200 petabytes per second based on the technologies that are available? If you look at DDR4 and say, well, what could we do with DDR4? If we were to make a memory system that delivered 200 petabytes per second with DDR4, the DIMMs of that memory system would use somewhere on the order of 50 or 60 megawatts, right? Just the DIMMs, right? We haven't actually done any compute yet.
That's crazy.
Right, so that pretty well told us that the memory system does not look like a DDR system, right? DDR5 improves that, but it's a percent change. We needed an order of magnitude because the goals of these exascale systems was to get them in the range of sort of 20 to 30 to 40 megawatts at most, total system power, right? Right. We're already over that budget with DDR4 by itself, right, without doing any compute. So about the same time, we were, working with some of our technology vendors on the beginnings of HBM, right? And NVIDIA began working on and put out HBM2 in their Pascal chips, right? Which was the first iteration of that we put in at a couple of sites to great success. And in fact, that's still running the fastest supercomputer in Europe, right?
Yeah.
Is based on those chips. And that was, HBM as a technology was one that we then took a look at in the same analysis. We said, well, could we do this 200 petabytes per second with HBM? And the answer is yes, absolutely, because the bandwidth per watt is an order of magnitude better, right? We could get there in maybe 6 or 7 megawatts of memory power instead of, 50 or 60, right? So that led us really early on in sort of this exploration space to focus on HBM as really the enabling technology for exascale, right? From a compute perspective, there's a lot of different options we could go to get there, but from a memory perspective, there was really only one choice. and that was to move forward with HBM.
Yeah. I mean, that makes sense. And that's kind of what's pushing us as well on the memory industry, right? To keep pushing this bandwidth, the pin bandwidth, going from HBM2 to 2E and to 3.
Again, there's going to be multiple points on this curve, right? Figuring out bandwidth versus capacity. And it's really looking at the workload and the needs of the capacity needs of that workload, and then how can you best get the best performance on that capacity. Honestly, this is the world's oldest computer architecture problem, right? Every time that we find gaps and and looking at memory levels and memory technologies, we try and insert new ones in the middle that better match or give us a better ratio in some cases, right? And it's that writ large, but it's per workload, right? And now we can start focusing memory systems on our workload, which is sort of an interesting architectural thought.
Yeah, and it's an interesting time as well, like you said, right? I mean, this isn't a new problem, right? If you look at that whole memory stack, the hierarchy, right? So it looks like now people are kind of pushing on both directions from DRAM, right? The Cerebrus example that you kind of touched on, it's pushing more towards bandwidth and reduced capacity, and then on the other end, people are pushing more towards large capacity persistent memory, and again for some specific problems, right? So it's a fascinating time that you're kind of looking as the problems become a certain critical mass in terms of its size, right? Then we as a memory industry as well look at new solutions to solve this newfound problem, right? So it's in that sense it's that fascinating interworking between system guys and processor guys and component guys like ourselves.
Yeah, and it's and all that. It's not just a power thing or a workload analysis. It's a cost argument, right?
Right.
If you find the most efficient memory system, you've found the most cost-effective memory system likely too, right? And that was another, we did the same analysis where we were looking at the power to deliver 200 petabytes per second. Well, we actually looked at the cost to deliver 200 petabytes per second. And everyone talks about HBM as a relatively expensive memory, and it is per bit, right? Per gigabit of capacity. But if you look at its cost per bandwidth, it's an order of magnitude better, right?
Right.
It's delivering with HBM2E 200 petabytes a second is an order of magnitude cheaper than delivering it with DDR4, right?
Yeah.
So it becomes a question of cost effectiveness of getting to the workload capability you need to get your work done.
Yeah, and that balance is always super important, right? And one other thing that is important in that balance is reliability and kind of high availability, right? And this is a problem for both supercomputers as well as the hyperscale distributed computers. So when you look at the reliability needs, right, and components, memory contributes a lot to reliability of a massive system. So and in particular, if you look at high bandwidth memory, it's an in-package memory, right? It's integrated with the GPU or the accelerator, and you can't just like in a DIMM, if a DIMM fails, you just replace that DIMM and everything goes on. But you can't do that with co-packaged memory, right? You've got to toss that entire SIP. So tell me about how your customers, and both on the labs and as well as enterprises, how do they look at this reliability problem? Because you can solve, and like I said, right, given unlimited resources, you could solve any problem, right? But cost is always the constraint.
That's a really good question, and it's a multifaceted answer because there's no one way to solve it, right? If you look at what a lot of our capability customers do, right, the ones that are trying to do the biggest problems at full system scale, those jobs are typically running across a large percentage of the system all together in a very tightly coupled way, right? From a software model, this is typically through something like MPI, right, message passing software, to do quick interchanges between sockets, and the time between them is very, very tight. And so this job is really tightly interconnected. It's really working on one problem across, an enormous amount of compute resources. in those contexts, if you have a failure on one of those in one of those sockets, right, in one component of that system, and that failure causes a system failure, it causes a application crash. So perhaps an uncorrectable memory error is probably the most relevant one for memory technology. Then that actually halts the entire simulation for the most part because of how tightly coupled it is. That's an enormous impact on the usability and the capabilities of these systems. And it's also sort of compounded by the fact that by making these systems so large, we have so many components that the odds of a failure start to get pretty high, right? Think about, perhaps the mean time to interrupt across a massive system, if you're running across the whole thing, is less than a day. Your odds of getting something like that. So our customers have actually adapted to this on their side by doing things like investing, right? They actually have to spend money to solve the reliability problem, right? One way they've done that is through checkpointing, right? So they put in some high performance storage component such that, every so often throughout their simulation, they take contents of memory, the data set they're working on, they pause for a couple minutes and they drop all of that state to storage, such that as they resume and keep going, if there's a failure in the system, they don't have to go all the way back to the beginning. They only have to go back to the most recent checkpoint. So this is a way of sort of mathematically figuring out how they can maintain forward progress on their simulations, right? And they've actually, it sounds almost kind of like morbid math that you could compute enormously and have a failure and actually get into a situation where you don't make forward progress, right?
Right.
So they've solved that somewhat from that aspect by doing checkpoint restart on failure. But even that is an investment, right? That's expensive to put in a high bandwidth flash subsystem, right? So this is something that you've seen in the burst buffer work from Los Alamos National Lab is probably the most, the biggest public display of that. But the other way that we've looked at it from a system perspective is to come call on folks like Samsung and say, how can we make these memory technologies more reliable? And to your point about replacement and the fact that replacing a DIMM is easy and not that expensive, but replacing a poorly performing or faulty piece of high bandwidth memory is extremely expensive because you're taking a multi-$1,000 socket with it. That puts a lot of pressure on two things. One, obviously, we want to keep the error rate as low as we can, but the other one is we want to be able to do things like repair in place, or find also software mechanisms to try and tolerate errors where we can. So those are things that we're working both directions, right? We're working with our customers to make sure that they have the right capabilities to make forward progress on their work, but we're also trying to get things done, in the industry on making sure that HBM, for example, is more reliable going forward in the future. We think it's at a place where it's usable now. We think it could be better, right?
Yeah.
That there are solutions, coming, over time to a lot of these problems. But right now we're in a place where we think it's usable. We think it's going to be productive. And we are obviously betting big on it, as we're going to see in these exascale systems in the next few years.
I mean, that makes sense. And it's interesting, right? Because on one hand, you've got this pressure of, extreme number of components. And on the other hand, Moore's law is creating, problems for memory structures themselves, right? So you look at what is memory after all, it's basically, charge stored in a capacitance. And as you scale, the amount of charge that's available, decreases rapidly, right? So we're at a point where, the entire industry has to solve this, and we're kind of looking to the HPC folks, right, to kind of push down some of these, solutions that you've talked about. One thing we're doing as component vendors, putting on-die ECC for a lot of the future memory and for the problem that you and I are talking about, right? So it's again, even here, this whole notion of hardware, software, co-design has to extend down, to not just performance and functionality, but also to kind of reliability and availability. So
Yeah,
that's pretty
it's a full
fascinating.
it's a full stack problem, right? We work with the memory vendors on die reliability and repairability. We work with our processor partners on trying to you know, make sure that their ECC solutions, for example, work the best with the memory vendor solutions and work well together, that they provide the system capabilities we need to understand and diagnose and do repairs. And then at the system level, we have to figure out how do we maintain system reliability and forward progress for applications. Right. So yeah, it's a system-wide problem.
Cool. So one, couple of final closing thoughts, then. This is a pretty fascinating discussion for me and, definitely for our, audience of GTC. So one thing, if I ask you to kind of take your crystal ball, right, and look at a macro level, you guys are building these exaflop systems. It'll be delivered in the next year or two. Beyond that, do you see, like, let's go to zettaflop cluster or even 100 exaflops, right? Do you see this current kind of CPU, GPU architectures as continuing to deliver what you guys need, when you scale this up yet another order or maybe a couple of orders? Or do you see, some people are calling for a shift away from von Neumann computing, right? What do you see in your radar? Obviously anything can be done, but, there's always the big issue of software continuity and developer productivity, right, while still delivering large scale systems. So touch on what do you see in future for these massive systems then?
Yeah, it's an interesting question because it's a difficult answer, and a lot of these challenges around Moore's law, the slowing rate of improvement, increased power and needs and power density have been reasons that this has taken longer than others. But we've learned a lot in the progress in the process. I think going forward isn't going to be easy, right? There are some steps that we can take in the traditional sense using CPUs and GPUs where we bring around, you know, just taking advantage of what we have left in terms of scaling, right? There's still probably a good factor of maybe 5 or 10 left there, at best is
Yeah, you're
maybe
gonna
the way
have
I
to
would put
count atoms now, right?
and then it's starting to look at focusing on getting the architectures tuned in ways that are interesting, right? Now you can think about whole hog new architectures where I take an accelerator that's just built for one problem and it's a brand new software ecosystem that maybe all you have to do is just, it's built for one program, right? Those architectures are actually, I don't want to call them easy because it's from scratch, but it doesn't have to wrestle with any of these problems. The issue is that nobody in the world runs one thing, or I should
Right.
say, the number of people that are running one problem and buying a large system to do it is pretty small. They all have variability, they all have variations, they all have workloads that are changing over time. And so you really need some amount of general purpose to really make a computing environment productive over time, right? What we're seeing in some cases, and this is a particularly interesting one in my mind, is innovations within the core of acceleration, right? The first inkling we're getting of this is things like the tensor core, right? That NVIDIA did to accelerate small precision, um, matrix multiply, right? It was something that adds a new capability, right? A really large chain performance uplift for those types of workloads. But the more interesting thing is it's all within the existing software ecosystem. In the memory space, it's again harder, right? We're moving forward and HBM is advancing. It's still a fairly young technology, but we expect that to grow as well. Um, you know, Getting to systems that are another order or two of magnitude faster is going to be a challenge um, that touches on all the areas we've kind of hit on, right? Reliability, programmability, right? A broad applicability versus trying to focus on specific workloads, right? Um, but I think what I will tell you is it's very, very unlikely that if we get to a zettaflop, that it will be a CMOS architecture. I think that's going to be tough. right?
Hmm.
It I'm not going to say never. Our CTO has, I think, been quoted as saying it won't happen. Right? On CMOS, I'm a little warier about long-term projections, but um, there's a lot of challenges.
Yeah.
I think there's still, in this 10 to 100x left past, the first tier exascale that there's some line of sight to, but it gets harder past that, right? And we're looking at non-von Neumann. There's, a lot of unusual stuff out there. There's a lot of hype around a lot of technologies that have a long way to go yet.
Right.
But I think the industry realizes that if we're going to continue on some of the growth curves we've lived on in a hardware sense, that there's going to have to be some hard thinking about how this all works from the bottom up. So
Yeah, and it's fascinating, right? It keeps us all kind of driven and motivated, because the problem sizes aren't getting smaller. I mean, the problem spaces are getting more diverse, right? We've got to keep pushing. So that's kind of interesting, and I want to close this, fascinating discussion as always, Dan. I mean, we've covered, all the way from application down to like, challenging industry to kind of even look at different materials, right? I think the key point that you kind of hit on that is that this is a full stack problem. And so we need to come up with full stack solutions, and the entire industry has to kind of collaborate, right? Because everything is now, moving way faster than what individually each of these, stack components moves. So that's a great way to kind of close our discussion. And I, on behalf of Samsung Semiconductor, I want to thank you for your time, and thanks, Cray and HPE for being a great customer and a partner. Thank you, Dan.
it's my pleasure. Always good to talk to you.
Thank you.